So yes, thank you for the introduction, Morgan. So I will talk a little bit about the ROS build farm, which we provide to the community, and the topic is like what it can do for you. But in order to know what it can do for you, it's important to understand how it internally works, what it actually does, and then you can see how you can benefit from that. So the build farm currently is available on build.ros.org, and it has basically three main tasks. The first one is like building binary package, which you all hopefully appreciate, that you can just install the Debian packages and don't have to build everything from source. And the second part is you can run tests before or after your commit, which will help you to make sure that your packages are actually working and pass all the tests. And the third part is generating API documentation and extract additional information from your packages, which we'll see later is helpful for the wiki, for example. So the first question is, why do we provide that as like a central service? It would be totally feasible that everybody from you just creates Debian package on their own and uploads them to a certain location, or you run your tests local or on Travis, or you can also generate the API documentation yourself. But the big advantage of having a central service providing that is you don't have to deal with all the setup and keeping this stuff running. It's just something you don't have to worry about. And also all the artifacts are hosted in a central place, so you know if I get the packages from the official ROS server, they have been built by the pipeline, you know exactly how the process was, you kind of know it's like an official binary. But while the service itself, the build farm, is central, all the repositories, just like traditionally in ROS, are federated. So we only maintain a very small set of the ROS packages, but the community contributes all of their code, and that's the important part. So we have to deal with like people hosting their code on various hosting services, GitHub, Bitbucket, wherever you like to have it. And people prefer different VCS systems. So Git is very common, but some people use Mercurial, SVN. Some people might even use Bazaar or CVS, whatever they prefer. So in order to like aggregate all that, there's one central location where we register all those repositories. It's like a database, a plain YAML file, which describes all the ROS distributions you know, like Indigo, Jade, Kinetic. For each of them, we have a long list of repositories. And we specify for each distribution what are the target platforms, so we make them available for Trusty or Xenial. And we specify where the repositories are, what's the URL, what's the branch we want to build up. For the released version, what's the exact version tag, and stuff like that. And this information makes it available then to then later process them. We'll see in the next slides. So the first thing is whenever you want to like have this service use your repositories and process your repositories, you have to actively register your repository. So you go to that repository and actually add an entry for your code so that build farm actually knows about it. Just a short example, like the index of this one just lists all the ROS distributions. Latest one is Kinetic, just a very simple entry. And for each of these distributions, all the repositories are enumerated. So every repository you've seen, for example, Catgen, has a doc entry, where's the documentation, has a release entry, where's my release repository, and has a source entry, where's the code to be built to run like CI, for example. And it also defines the release platforms. For Kinetic, for example, we currently support Ubuntu Wiley and Ubuntu Xenial. So the high-level view on like building your code is pretty generic. You first get your source code from somewhere, then you have to make sure that you have all the dependencies in order to be able to build. Then you build your packages, usually a CMake make install pipeline, and you usually want to run your tests to see if it's actually working. And then the less common cases are you want to package your code into a Debian package, or you want to generate API documentation from that. We have like a tool which does the API documentation for you. It abstracts if you're using Doxygen or Sphinx or any of the other tools. So some more detail now, how do we do the build? So first of all, when you want to build like some software, you need to have the right environment. And the problem is, if you do it locally, you already have all dependencies. So locally it might work for you, but to start from scratch, you first have to get all the right dependencies. So in order to know that we have all the right dependencies, we try to isolate every job from each other. So every job on the build farm runs in its own Docker container that ensures that we always start from a clean slate. So you know it's a clean Ubuntu standard installation, and then you install what the package defines as dependencies, and then you can actually compile the package. That's a less common use of Docker. Usually people think for Docker like, oh, I can get an image of some certain application or use case, and you use it as like a distribution for your application. We only use it for like the isolation part. So every Docker container we generate is basically, I'm not saying a throwaway container, but we create it on the fly, build it, and afterwards we do not necessarily need the result or push it to a public repository. Also, when you think about building code, we usually build a lot of the jobs per repository, and that means you can have more than one package in a repository. So in that case, you have to know if there are multiple packages, in which order to build those, because you cannot build them in parallel from the beginning. Usually you do that as you do it locally. You create a Catkin workspace, get the repositories, and then you call something like catkin make isolated. We also try to like call the install target. Sometimes the package doesn't have one, so we cannot really, we can just ensure that you have an install target and you install some files. If that's all the files, that's up to your regression. And every time you build and run your tests, they generate something in a JUnit compatible output format, which makes it possible to generically read the output and interpret it if all the tests have succeeded or not. The important part is, for this, it would be perfect if we would have one container for every package. But that's a lot of overhead, so usually we only use one container for your whole repository. That it's good for us because it's more efficient. We don't need that many machines to have too many Docker containers. But the disadvantage is if you have two packages and they both need a certain dependency, but only one declares it, then the other one transitively depends on the other package pulling it in. That might work for some job, but not for others. We will see later. And when you write like ROS code, you probably also notice that the package itself had different dependencies, which can sometimes be really annoying if you have too many different types. But the biggest differentiation is the build and test dependencies for this case, because some dependencies you only need to test your code. And in order to be still lightweight, if you don't want to run your tests, we differentiate them into build and test. We'll see that later in some of the jobs. The previous slide mentioned that we build on the farm packages with catkin make isolated. I don't know how many of you use that locally. I think the most common one is that people use catkin make. So why are there two different tools? I will just compare them a little bit, that you have an understanding what's the difference and what the pros and cons of both of them are. So catkin make is basically one invocation on your workspace, and it calls CMake exactly one time. And that's good because all the CMake finding packages and dependencies only runs once. That's a little bit faster. But on the other hand, since everything runs in one big CMake context, targets have to be unique. So you cannot have two packages with the same target name, for example. Or if one package depends on the target in another package, you have to declare that dependency explicitly, even if it's like another package and it should be finished by the time you get built. Also, when you think about where things get installed to, one package might contribute its header folders and declare that that's the include directories where the headers are found. The other package might just drop the headers there, but doesn't actually mention it. But magically they get found because another package declared the correct dependencies. So there are some side effects you need to be aware of. The big advantage of that, it's really fast because CMake and then make afterwards can parallelize across all your targets. So depending on how much code you have, it can actually build faster. On the other hand, we have catkin make isolated. It invokes CMake for every package separately. So you don't have to worry about cross-package dependencies because when your package A gets built, B is already done. So you don't have to worry about that. And that provides a cleaner separation because each package gets processed on its own without side effects. It's usually better to identify problems because if you have been relying on side effects with catkin make, that will just like show, probably with a compile error or another problem. It's a little bit slower, but it's cleaner for like something like the build farm because we want to have like really good predictability. So because of that reason, the build farm always builds in isolation. Another aspect the build farm is doing, it builds only with one thread. You would say like, well, that's really slow. That's true, but if you've ever tried to debug the build output with J8, it can be really bad. So in order to make it easy for people to read the build output, the build farm just builds with J1. And you will see later we have so many jobs, we can scale on the number of jobs. We don't have to make one package run as fast as possible. So now I want to look at the first category, how to run the tests before or after your code changes. So the job type is called a devil job because it's basically used in the normal development cycle. As an input, you use one source repository. It comes from the distribution file we saw earlier. It tells us this repository is on GitHub, called gen message, points to a specific branch. And the devil job checks every hour currently, pulling, and it clones the repository if there are changes, and then it runs 2 Docker steps. The first one is, in the first Docker, it installs the build dependencies, it builds your packages, and then it runs installation. If that one succeeds, it tries the next round on a new Docker container. It installs the build dependencies and your test dependencies, then it builds your tests and actually runs your test. And the outcome of that can be like a simple light, where you have a failure, something failed to compile, you missed to declare a dependency, which is pretty common, we'll see later. Or the result can be yellow, like a warning, the job finished, but there are some issues. This can be CMake warnings, compiler warnings, some of the tests failed. Or if you're lucky, everything is green. In the case it's not green, you will get an email, at least if you have in your package manifest written your email address as the maintainer. So if you're not the maintainer, you will not get the email. On the devil jobs, additionally to everybody who committed since the last time the job passed, it was green, they also get an email. So that's good, and I'll get later to the point that you should care about the emails the build farm sends you. A variation of the devil job is you don't want to do it after you have committed. That might be already too late if you introduced a problem. So a variation of the devil job is the pull request job, where your repository, when you register it with this red flag, test pull request true, and you're hosted on GitHub, it will actually check if there's a pull request, and as soon as you create a pull request, it runs that integration job for you. And immediately it reports, after the job has finished, to GitHub what was the status. So you know before you merge a pull request, your own or somebody contributed it, if it actually passes your build and passes all the tests, which is very powerful. Currently, the pull request integration on our build farm only works with GitHub, simply because we have not cared to implement it for all other platforms. If you're hosting on different platforms, there are alternatives, or you could contribute to the build farm to extend it to, for example, Bitbucket. Another constraint is that the GitHub user Jenkins uses to report back the results needs to have access to your repository. There is a description on the wiki which tells you how to allow the GitHub user from Jenkins to access your repository. If you're in the github.com/ROS group, for example, that happens for all the repositories already. But if you happen to host it somewhere else, or you just don't want to give access to that user to your repository, you can run the same logic or the same behavior on a different provider. For example, Travis. So if you just want to use Travis, there's examples for that one also on that page, where you can just create a .travis file, and then the same logic as it runs on our build farm will just run in Travis. And that will work for any other provider. You don't have to use Travis. The second category is API documentation. And the process is very similar, just the build process looks a little bit different. Again, we will document everything in one repository, which comes from the doc entry in the distribution file. We only check that every 3 days because commonly it doesn't change that much. And it keeps our resources down. We clone the repository, and then a few separate steps happen. If you have written a changelog file using RST, we will transform that into a nice HTML document. We also extract meta information, so all your package names, your dependencies, maintainer information, author information, license, everything you can imagine. We try to extract that from all the different places and put it in one YAML file. We'll see later how that gets displaced in the wiki. And a very important step, we allow you to do cross-referencing. So if you have one package being documented and later you document a second one, you can actually reference API documentation in the other package, vice versa. And that's very powerful, and that's why I think the central approach for making this documentation is better in this case, because you can do this kind of things. For the actual process, in Docker you will install your doc dependencies, because sometimes you also have additional dependencies only for documentation. You expand your message and service files into Python and C++ code, for example, and then you invoke ROS.doc Lite on each of your packages. The same result as the previous one. The warnings in this case is usually from documentation. And there are two outputs generated from that one. First, we update the index for further packages to cross-reference with yours, and we upload the resulting documentations to a web server. Usually when you go to docs.ros.org, you will find all the documentation for different distros and all the packages available. And that's the nice result if you think about this wiki page for ROS CVP. I mean, the wiki page goes further, it just took the top of it. And all the information you're seeing is not handwritten. That's all like generated from the information already available. So you see ROS CVP is in the same repository as ROSCon, with ROSCon with a lot of other packages. You see the description of the package, maintainer, status, license, links to the repository, links to the code API and the message API, and very nice, you also have links to the Jenkins jobs. So if you ever worry like, oh, is my Jenkins job for a certain package working? You can just go to the wiki page and then find the link very easy. And all this by just writing a single line in your wiki page. So the only line you have to write is package header and the name of your package. And that gets all expanded if your package has a documentation job. Now the third category of jobs, which is like creating binary packages, which is probably also the most complicated one. So just from a first high-level view onto the release process, you're starting with your code in a source repository. And then you can use whatever tool. For example, cat can prepare release, which actually sets the version number to a new version and tags the repository. That's just your upstream release. And then you use the tool Bloom to create a release repository. What does that do? We will see in the next slide. But it basically creates the additional things you need to create a binary package. Debian control files, etc. We'll see about that in the next slide. Also convenient, Bloom will create a pull request to the ROS distro repository we saw earlier. So you don't have to handwrite that entry. Bloom will just create that entry for you, and when you hit yes, we'll just create the pull request for you. It saves you a lot of time. From this release repository then, our build farm will start building Debian source packages. I'm just saying Debian source packages. We can also have non-Debian packages, but Debian is usually the one we support most. And these source jobs work not only once per package, but they do it for every operating system, operating name and operating code name, which we have. So example, Ubuntu Xenial and Ubuntu Wiley need two different set of meta information, for example, for the control files. And afterwards, these source packages get built into binary packages by the binary jobs. And they are, beside being specific for the specific OS, they are also specific for your platform. So AMD 64, i386, ARM-HF, whatever you want to imagine. A short note on Bloom. You start with a source repository which has multiple packages on a single branch. And what Bloom does, it actually transforms one part it into a release repository where each package is gets only snapshot. You don't care about the history. And it's on a separate branch. So you first separate all your packages out. But there's more happening, otherwise we wouldn't have a tool for that. So it looks at your package, and the manifest contains information like the build type, build dependencies, run dependencies, a changelog file, etc. So in order to get to the point that you have a Debian control file, a Debian changelog, a Debian rule file to decide how to actually make binary packages of that, Bloom transforms these information. So if you have a build type which says this package is a CMake package, Bloom knows what the right recipe is, what it needs to put in the rule file to actually build the package. And when you have build and run dependencies, it uses ROSDEP to map those to a system package. And the last step we saw in the previous slide, it converts your changelog to HTML. And all this specialization happens for each target platform. So it's not like one package results in one entry in the release repository, but it's specific for each operating system you actually target. And why do we have that tool? It's all about automation. You could do all that by hand, pretty painful process every time, but it makes it just much easier to use a tool to release packages easily, because you don't want to bother about the details every time. Bloom also allows you to apply a lot of customizations if necessary. In 90% you might not need that, but when it is necessary, it helps a lot in like doing the change one, and Bloom will reapply the change every time. And as mentioned before, it will create the pull request for you. Now looking at the source deb job, we start with a release repository which was populated by Bloom. And that actually gets checked very frequently because we want a fast turnaround on that on new releases. So every 15 minutes, if you have actually changed your version number, It clones the specific package branch from that repo. In a Docker container, it installs all the necessary tools to build Debian packages. And it uses GPB build package to actually produce the source deb. There's no orange state in this one. It's either green or red. There's no in between. If it's red, you will get an email. And the result, again, gets pushed to an apt repository. It's one of the servers where you find the final repositories and the final packages. And additionally, it triggers all the binary packages for that, all the binary jobs for that package. The binary job then does the next step. It takes the source deb, fetches it from the apt repository. Well, there could be reasons why you want to abort here. Maybe the dependencies have not built yet, so you will abort now and retry later. You add a timestamp, so every Debian package we generate has a specific timestamp that you know when it was built. And then within the Docker container again, you install the build dependencies as described by the Debian control files, and then you build the package. And again, you get an email if it doesn't work, and the result gets pushed to the apt repo. And since ROS1 does not guarantee ABI compatibility, we don't force you to do that. We highly recommend you try. But if it's not ABI compatible, when you build a package, you also build all the downstream packages just to make sure that they still work. Now looking shortly at the repositories where the code actually goes after that one, you have the main repository you might be all using when you get your Debian packages. packages.ros.org/ros/ubuntu. There's this repository before, it's called the testing repository or shadow fixed. That one is, we populate that first, and then we let people try it if they're really brave and want to try that repository. And if everything turns out to be fine, then we give it to the big public. It's basically kind of a staging thing. And we make this decision when it's time to sync manually. Behind all that infrastructure, where you should only use the public one, there's another set of repositories which is closely located to the Jenkins farm to have fast access to it. And there's a repository before called building, where you actually on the fly build new packages, remove old ones. You should never use that one directly, but the build farm just needs that one to operate quickly on those. And then if everything was built, it goes to testing, and that just mirrors to the public repository. Now with all these packages building, it's sometimes difficult to see what package is actually there, what has changed since last time. So there's a huge amount of information which is visualized in the status pages. You can take a look at repositories.ros.org/status page, and there are entries for various different groups of packages in each distribution. So, and they will show you in each of the three columns where you see the three squares. These are the building, testing, and main repositories. And if they're all green, that's good. They all have the same version. If they are, in this case, the fourth line has blue, that means, oh, there is an older version in the public repo, so whenever we're going to sync next time, there's going to be a new release available for everybody. And if it's red, that means there's currently no version, and if it's not yet public, that's not a big deal, but if the first column would be red, that means currently it's not building. So it helps us to get a good overview about when is a good time to sync, what are the actual changes. Yes, and I already said that one. The important part here, if you go to this kind of status page to see if your package was building, is it already available to everybody or only finished building on the farm recently, the first square in each of these columns gets you actually to the job which builds the binary package. So if it's red, it's really good to go to that job and look at the output to see why it's actually failing. If you look at the Jenkins farm at some point, like build.ros.org, you will see a lot of jobs. We'll see the statistics later, but the job names are not that easy to read sometimes. So just as an example, they are separated in three parts. The first part is like a prefix. It allows us to group different jobs to make it easier for us to navigate this huge number of jobs. And each of these prefixes ends up to be a tab in the Jenkins UI. So you can easily go to the kinetic binary jobs for Ubuntu, Xenial, 64-bit. That's basically the first block. And then you have the package name or repository name as the second part of the name, and then the full expanded platform and operating system and type of the job as the suffix. Why do we have these complicated names? It's just the number of jobs. So if you look at our Jenkins farm, we currently have almost 41,000 jobs being configured on that farm, and we don't configure them by hand. They get generated automatically. And the very good news is, 97% of them are just passing, right? That's good. There are some cases where, for example, in this line, the orange one, on RMHF, some of the jobs are disabled because we just can't build all the 2,300 packages in Indigo on RMHF just because they don't support RMHF, and that's okay. And you see some of the development jobs have failures, so some of the repositories are registered, but they don't compile or have other issues like wrong dependencies. So these two colored numbers are the things we try to like keep down as much as possible. And each distribution has different numbers. Kinetic is very similar. The only difference here in Kinetic is that in Kinetic we enabled that if you run a CI job, it will actually tell you if there are compiler warnings or if there are like CMake warnings. So that's why the orange number in the third column is like a little bit higher, because more jobs get flagged as, oh, there is a warning. You might want to look at that. Currently we host the whole Jenkins farm in the Amazon cloud. It's one huge, really beefy Jenkins master, a web server for the repositories, and then always 2 nodes compiling code, and we can scale it up to as much as we want. And as you imagine, it costs money to run the farm, so probably $1,000 to $2,000 depending on how much load we have in a month to operate all those machines. And that's just like the cost for the hardware, not the time we spend on it. As a number of scale, in September we ran on Jenkins roughly 80,000 builds, and that equates to roughly 10,000 hours on a machine of work. But you don't have to necessarily use the build farm in the cloud. It's all written in one Python package called ROS build farm, and you can install that one on your Debian as a Debian package or using PyPy. And you can run all these jobs I described before, the devil job, the doc job, the release job. You can run them locally. And the blue links are actually like links. If you get the slides later, you can look to more documentation, because these scripts have quite some arguments to get them right. So it's not that straightforward to like just invoke it with no arguments. But it helps you if something fails on the farm to just reproduce the same result locally. Because it's all contained in a Docker container, you can be on a Xenial system and still run the jobs for Wiley, which sometimes helps for debugging. One scenario which the build farm currently does not support you that well is if you want to test across repositories. So consider the scenario where you make changes to 2 different repositories. The first one you add API, the second one you want to use the API. The devil job will fail because A will pass, but the repository B will fail because it's still using the last released version of A. So that's one of the cases where it doesn't help you testing. Or think about you make a change in repository A, which breaks tests in repository B. Since we only test on repository level, you will not see that until you actually release repository A, and then it's pretty much too late. So in order to use these kind of like more complicated scenarios, there's another category called pre-release jobs. And what a pre-release job allows you to do is you're not only selecting one repository, but you can select n repositories to build from. So from multiple repositories, you take the development branch, and the job then installs all the dependencies from Debian. That's what you saw as a devil job, just with more than one repository. And you can additionally select another set of repositories which you want to ensure that they have not been broken by the changes you made in the repositories in the underlay. And again, you need everything in between also from source, because it might affect how it's being built. Additional stuff you can get still from Debian packages. This is the concept of a more complicated pre-release job. Oops, I think I forgot something about that one. Yes, since the pre-release job also has lots of arguments, there's actually a website where you can generate and configure in a nice UI like what repositories you want and what dependencies you are interested in on pre-release.ros.org, and then it generates a command line which you can then run locally. You can go really crazy. You can make the workspace like almost every repository of ROS Indigo, but then expect it takes a little bit longer to compile. Currently, the supported platforms from the build farm which we can produce is we can build stuff for Ubuntu and Debian. We can build for AMD 64, i386, ARM64, and ARMHF. But since you could have arbitrary combinations of those, and there are many Ubuntu distributions, but we just can't cover all the combinations. Not only because of the cost for the infrastructure, but also for the time we have to spend on like troubleshooting if something doesn't work. So for example, in Kinetic, we have a set of Ubuntu targets, Xenial and Wiley, where we only aim the 64 and 32-bit platforms. And we select the ARM platform's only for Xenial. So for example, we don't build the ARM the ARM targets for Wiley. And on Debian, the list is even shorter. We don't build 32-bit packages for Debian, for example. The tool Bloom we saw before also generates the meta information to do RPM packaging, but we do not build RPM packages at the moment. There was community contribution to build them manually, but that has not been integrated in the build farm yet. So if you think, oh, we need to like build a certain kind of binary for a not yet supported platform, you can always come and talk to us. If you donate like resources in terms of CPU or even just like troubleshooting resources, that always helps us to justify adding more platforms. And if you are willing to like, if you want to, for example, automate the RPM process, it's always possible to contribute that to the build farm that can be done in the future. Or if you are like usually in a company where you want to build packages for different combinations, or you want to build private repositories, you might not want to use our build farm because everything is public, then you can also run your own build farm. And for that one, you need two different steps. You first need the right machines, so provision a Jenkins master, Apache server, and all the nodes doing the computation. And then you actually need to generate all the jobs. And there are really good instructions for doing that. And originally, Bosch was the first company which we worked with to get that build farm up and running. There was a presentation last year if you want to like see more details about their build farm. ClearPass is also using that, but we hear from Mike that there are upcoming alternatives in the next talk. But if you run your own build farm, you got to be aware of you will have continuously have to monitor things, because at that scale, usually it's not something which runs smooth 100% of the time. So if you now want to leverage that, so what can you do to actually benefit from that? You should just register your repository. If you want to have documentation, and I just encourage you, you should have documentation for your package, at least the minimal thing we saw before in the slides. If you don't write more manual, you add a doc entry to the distribution file, and that helps you when you create a wiki page, which you should also do for your packages, to have at least the overview. Where is the package located? Where's the repository? Where are the jobs? Have some basic information about the code API and the message API. You should also have a source entry that allows not only for the devil jobs to run, or potentially for pull request integration if you like, but it also allows users to easily clone your code with, for example, ROS install generator. They specify a repository name, and it just like magically clones it because it knows where it is. If you happen to have a repository which, for whatever reason, doesn't pass compilation on our farm, you should still register it and say, I don't want commits to be tested. That at least still allows users to clone the code easy. And of course, you should have release entries if you want your code to be packaged as Debian packages. One important thing, if you register your repositories, you should really watch out for the emails Jenkins is sending. Try to read them, try to look for the problem, and try to fix it. If not, just ask a question. We are happy to help getting your job to pass. I mean, it's in our interest that we don't get too many jobs passing. As a last resort, if there are criteria, for example, your package doesn't build on ARM, there are ways that we can disable jobs or blacklist targets, which will just avoid you getting spam emails for something which you know is not working. Some hints for like troubleshooting, because that's like usually the most common cases we see people running into. The argument is like, oh, but it works locally. If I compile it, the job does something wrong. So usually there's something different about it. So it can be that you use catkin make, and catkin make isolated behaves with the side effects we saw before a little bit different, and it doesn't work in that case. So you might want to try that first. It can also be that you have a dependency installed on your system because you're already working with it for long, but the build farm doesn't know about it because your package doesn't declare that it needs that. And since we're in a clean Docker container, it will not have that dependency. That's usually a very obscure CMake warning when you see, oh, it can't find a certain package configuration, which is not that great, but no, CMake. And the next one is the devil jobs, where you build multiple packages in a repository. That one passes, but when you actually package it into a Debian package, it fails. And that's commonly, one of the common reasons is that the devil job installs all your dependencies from all packages, whereas the binary job runs per package. So if one of your packages has a dependency declared, the other one just like relies on it being there. That might pass in a devil job, but might not, and will very likely not pass in a release job. So check out the dependencies of each of your packages that you actually declare the right thing. And then one of the things we sometimes hear, we try to like do our best to avoid that, but there are hiccups on the farm. If you think about like 80,000 jobs in a month, there are things like GitHub server doesn't reply in time, you get a timeout on a simple HTTPS request, or just GitHub has a really bad like day and goes down for an hour, then our farm is going like really wild. And it can send out a lot of emails. But that should be the exception. So sometimes you get an email that something is like bad and you can expect that if it's an upstream problem like network, it will fix itself. If it doesn't fix itself, it's probably not a hiccup. It's probably related to your code. So always try to look at that one. And if you get too much emails, always try to look into that you actually not start ignoring those. Over the last year or year and a half, we did a good amount of work to reduce the number of false positives you get. So we really try to like not spam you with those emails. Since the slides contained a lot of links, you can go to the slides if you want. There's also additional information in the package documentation itself. You can follow up with them, especially to run the jobs locally. There's extensive documentation. And I'm happy to take questions. Thank you for your attention. You don't have to ask questions. Nope. Oh, so the question was like, how much machines does it take to keep us like running? Well, so we always have a minimum set of 4 machines, one for the master, one for the app repository, and 2 machines building. And each of the building machines can run up to 4 jobs at the same time. So it's 4 core machine, we run single threaded, so like that's the minimum we always pay, like 24/7 basically. And then when we actually do like a big release, like usually when I do a Catkin release, that means no ABI assumptions, so we build everything new. So for a Kinetic or Indigo release, that means we kick off like 8,000-9,000 jobs. And usually we host them in the Amazon cloud that there's something like called spot instances. You don't pay for the full instance, you pay like a fraction, like a tenth of the normal price. The disadvantage is they can take the instance away anytime you want. But since we can just recover and restart the job, it's cheaper for us. And we scale up to like sometimes 12 additional machines, for 15 additional machines, which means we run like 40, 50 jobs in parallel. And for example, we did a release recently to Kinetic, and that one pushed the farm with like 50 machines for like 2-3 days to build all the different platforms. And usually the ARM platform is the slowest because we use emulation for that. So all the other platforms usually build in like 1 to 1.5 days, and then the next 1.5 days you're catching up with ARM. Yeah. All right.
Thanks for this presentation. One question which might be the source of a future talk, I don't know. This is very Ubuntu and Debian specific, and I wonder how this looks in a ROS2 world when we add like Windows and Mac support.
Well, we should just use the Ubuntu in Windows thing. No, kidding. No, I mean, the goal is to support it natively, for sure. So we're interested in having, I think, at some point, chocolatey packages, which are like the package manager supported in Windows 10. There hasn't been no work on that part, but I think the process pipeline that Bloom could generate the necessary meta information to make chocolatey packages would need to be extended, but I think the pipeline would be very similar. But yeah, for Mac OS X, that's a good question. William might have a better answer than, because I never use OS X. But for Windows, I think the chocolatey packages are the straightforward way. And for RPM, we've seen the contributions from the community to like be able to build them. So Bloom does the necessary steps for you to have the meta information, but we haven't automated the process to actually generate the Fedora packages for that. But I think that's definitely in the interest of the community to support more platforms.
Thank you.
Okay, I repeat the question because the microphone is a little bit... so the question was like when you do the manual syncing from the shadow fixed repository to the main repository, which everybody sees, is that like sync everything at the same time, or is there some like mechanism to like sub-select what we want to sync? So there there are two different kind of packages, categories, I would say. There are the core Python packages, like Python Catkin PKG, Python ROS distro. They are across our ROS distributions. So we cannot only deploy them to Kinetic. So they get deployed for all of them. But all the other packages you see, like ROS-Kinetic-name of the package, we sync them by distribution. So while we have to make sure that at the same time we don't shuffle the apt repository while we do the syncing, we just decide Kinetic is fine now, we tested it for a few days, and then we sync all the Kinetic packages in one block to the new repo. Yeah. Usually that happens per distro on a discretion, like when there are enough changes and when you're certain enough that you have done enough testing. So it could be that sometimes a build finishes and we sync immediately because there were no big changes and we are very confident it works. And recently for the Kinetic release, we actually sent an email beforehand. We're like, oh, there were like some significant changes. If the community can try them, give them a few days more. We actually tried like 1.5 weeks. People found regressions, that's why we do that. And then you do another build, wait another more days, and then you make the decision when it's actually comfortable to sync.